advancing. Give me a second. There we go. Okay, so welcome back, everyone. So this session I've called Deconstruct Everything. And we're going to talk about where bias might be hiding and what validation really means. And I've made up a different company called Absolute AI. They're defeating aging through big data by using AI, big data, unique signatures of, blah, 99% accuracy, novel drugs, $100 billion. I mean, this is not a real company, but it seems like a real company, right? I'd say there's many types of companies like this that I've seen, and I've kind of amalgamated them all into this example here. So let's start by talking about AI and what does AI actually mean. And full disclosure, I'm not an AI person. I'm a biologist by training, but I've come to accept a few frameworks again for how I think about AI. So what do you want it to mean, right? That's the first thing. AI these days means everything, and that can mean nothing. So I've come to think of AI as a term that vaguely means I do data things on the computer, and that could be as simple as a regression, which require continuous dependent variables, and then you have linear and nonlinear regressions, and then each time you have new data, you basically just add another point on the graph, and the regression line changes slightly. And then now you are learning from inbound data, and you call that machine learning because your regression line is changing slightly every time you have additional inputs. Yeah, okay, you could call it AI or machine learning, and there are parts of machine learning that require a lot of statistics. We'll talk about that in a second, but I think we typically think about these general types of linear and nonlinear regressions that we learned in algebra class and multivariate back in the day, right? So you see some terms thrown around here just for everyone to be caught up at the same level. R squared obviously needs to be as close to 1 as possible. Everybody knows that. What it actually means is the explained variation divided by the total amount of variation. So if you think about, for example, this regression line, and think that it's much fatter to encompass all the explained variation. If no dots fall outside of that fat line, then you have a perfect one. And another term that's quite common that I think I just want to explain here is the confidence interval. I think people hear about confidence intervals a lot. If you don't know what that means, it's very simple. It's a range of values in which you think the true mean likely lies. So in plain speak, if it's a 95% confidence interval, it just means you are 95% confident that the true number, the truth, lies within this range. And so sometimes with these regression lines, you actually see the confidence intervals also mapped out as dotted lines along the side to show that you think that this is the right regression line within 95% confidence intervals. All right, so moving on to machine learning. So this is pretty similar to basic regressions. So what most people mean by machine learning is statistical learning. So you still take in data and you use statistical analyses and apply them to the data set to do what you want, like categorization. So in this case, the regression has a categorical dependent values instead of contiguous. And this example shows that samples have features extracted, fed into some classification algorithm, and then output into these disease or healthy groups. So remember that the classification algorithm is basically a bunch of statistical formulas, right? So what we call machine learning is the application of a variety of these statistical models, including regression models, to create these classification systems. And when you think about classifications, these are typically logistic regressions, not linear regressions or nonlinear regressions. And there's multiple types of logistic regressions. A binary logistic regression splits things into two categories. This is the most common, I'd say, that you see in biology, which is healthy versus disease. An ordinal logistic regression stratifies the input samples into related groups, so they have to be linked, so mild, moderate, severe. And then a nominal logistic regression splits into many categories that are unrelated to each other. So different types of diseases. So you input a bunch of different sample types and it spits out this person has lupus, this one has Alzheimer's, this one has cancer, etc. And so you're able to use these regression models to separate out the blue from the green. And this is obviously a very simple explanation of machine learning applied to creating a binary categorization. But there's way more complex ways to visualize these different types of logistic regressions. And we'll talk about that in a second. In terms of deep learning, right? People say deep learning, neural nets, all of that. The difference is that a computer does more and a human does less. So it's very similar to the previous example of machine learning, which I think is the broad category, and deep learning falls into that. The difference again is that machines are doing more, so humans are doing less. And so instead of doing humans doing feature extraction, for example, the computer is doing it for you. And so you have less human bias, but maybe more computer bias. And there's a bunch of features that people wouldn't see, but computers might. So just a quick example of how computer bias actually falls into deep learning. The earliest incarnations of AI, so real AI, so like neural nets for X-ray data, was very interesting. It was an application of deep learning to detect disease from X-rays. Simple, right? You feed in tons of X-rays, doctors annotate to say this is disease or not, so you train your neural net with that, and then the neural net spits out different categorizations, disease versus healthy. But the fun thing was that in these earliest incarnations of AI for X-rays, these algorithms were able to pick up differences in X-rays depending on the actual instrument manufacturer. So a Hitachi versus a GE X-ray machine would be classified into disease versus healthy. So it could be the same patient, just two different manufacturers of the X-ray, and you just have a different classification. And that's an example of computer bias, right? A doctor would never look at an X-ray just because they're done on two different machines and say that, oh, this is healthy and this is disease. If it's a disease patient, you're just a disease patient. But a computer picks up things that you just never would expect a human to be able to pick up and then use them for classification. So training is very important, but it's just an example of how computers can also add bias in deep learning. So those are images. That example was images, and that's very simple to think about how you train a deep learning algorithm. But in biology, you don't really see as much deep learning, I'd say, and that's because of one simple thing, right? The concept is that feature extraction, this part that you let the computer do, is actually built into sample prep for most biological applications. So when you think of a sample as people, it's not really people, right? You're collecting a particular analyte from them. So you draw blood from people and you're looking for proteins or RNA or DNA. But when you're doing that, you're removing everything else and you're just extracting the DNA itself. So you're physically removing all features except for the analyte. And so there's not much that a neural net can add in terms of feature extraction. And that's typically why, for a lot of companies, when they say they're using AI, they're talking about more traditional machine learning and not about neural nets and deep learning methods. So you've fed all these things in, you're digitizing a biological signal, and you're getting these disease and healthy outputs, but you're not necessarily using a neural net. So I'm not an AI expert, I'm a biologist. So I always say, okay, how do I figure out if a company is full of crap or if they're using something real? I start by looking at the output and the input before digging into the actual AI of things. So if the output looks bad, then why bother digging deeper? And if the output looks good and the input actually checks out, then there's some magic happening, and that's when you sit down with a team for a high-level overview of what their algorithms are actually doing. And when you actually unpack what these algorithms do, typically they are just very basic statistical concepts like regression models that are, not just one necessarily, but things that are kind of stacked on each other. And you can gain a general understanding of what a company is doing, even if you're not an AI expert. And that's typically how I have to diligence these things. So we talked a lot about output in the last session. So let's talk about input, right? So if an output looks good, great, let's move on. So in the case of Absolute AI, or anti-aging company, they said that they've trained their algorithms on 200 patient samples, used over 2,000 microRNAs, 20,000 genes, and validated on 2 million individuals. And yeah, I mean, I'm lazy. I just used orders of magnitude here to illustrate a point, which is that a lot of times big numbers can be thrown at you, but it's not necessarily big data just because the numbers seem big. For example, here we're talking about 200 patient samples. Everything else is fluff. I mean, it's important fluff, but it's still fluff, and I'll explain why. But we're not talking about big data in a traditional sense here because it's 200 samples. So this is where you need to unpack the actual data itself and figure out if the fluff is real or not. So sometimes big numbers seem great, but they're not. Let me talk about a few ways that big numbers might not actually be that great for a company. So in this case, Absolute AI said that they use 2,000 microRNAs and 20,000 genes. Let's just ignore the microRNAs because I don't want to have to explain what those are. But when we talk about 20,000 genes, everyone knows about genes, right? But do we actually know what they mean? Companies can mean a lot of things when they say they're using genetics and genes. Do they mean DNA, RNA? Remember that genes are DNA, and many times people are actually talk about gene expression when they say they're measuring genes, which is RNA, right? So each gene, each piece of DNA creates hundreds to thousands of copies of RNA. And so when you say, when you hear somebody say that they're measuring the expression of 20,000 genes, you probably have to multiply that by many thousands, hundreds of thousands, potentially, to figure out what the absolute number of molecules they're actually trying to detect are. So I'm not gonna explain this, but the data looks very hard to interpret. This is a heat map of gene expression where the columns are genes. So each of these columns are genes, and the rows are people. And the color in general is for gene expression, red meaning high expression, blue meaning low expression. But the point is that the data sets are complicated, and if you're collecting data on 20,000 genes, that's 20,000 variables, not to mention the absolute number of RNAs that are actually produced by each of these genes. So when is bigger not actually better here, right? It seems like a lot of data and you can do a lot of great things to it, but more variables leads to overfitting all the time, right? You can tweak the variables as you need and weight them differently in your algorithms, and you can gerrymander, if you will, your sample so that you are perfectly picking out disease versus healthy. And that happens all the time. Overfitting, I'd say, is a bane of my existence when it comes to diagnostic companies. And sometimes the companies don't even realize that they've overfitted. They think that having more variables is actually better, but really more variable leads to your algorithms being so fine-tuned that you can overfit to any data set. The other thing I want to mention is that having more variables can be impractical from a clinical sense. So, measuring this many genes, great, except it's very hard to do a lot of times, right? It costs a lot to measure more genes. And it might seem like the company did a lot, but in this case with Absolute AI, the company's probably using retrospective data, and we'll talk about that later. So they didn't have to do the hard work collecting all of these different variables of different genes and their expression levels. So there may be real life constraints like cost, time, finicky technology that makes it actually impossible to get all of these different variables. Basically, it makes it impossible to measure 20,000 genes and 2,000 microRNAs every time you want to test a patient for something. maybe the technology is just not that good, or maybe the technology is super expensive, or maybe it takes 3 months for a result to come back because it's, you can measure these things, but it just takes a lot. Maybe it costs, $20,000. And all of this makes it highly, highly improbable as an actual product at the end of the day. And by the way, more variables means that there's almost certainly more bias. And I think this concept is actually counterintuitive for a lot of people. How can more data mean more bias? A lot of times you want more data to get rid of bias, right? The more you know, the more enlightened you should be. But that's not always true. So let's talk about where bias might actually be hiding. So this is a genome that you can sequence. Oh, it's a human genome. I don't know if it's an actual human genome. Let's just call it a human genome. And so a human genome has roughly 6 billion base pairs, right? And if we talk about sequencing a whole genome, a sequencer has 99%, maybe a little bit more accuracy. We'll just call it 99%. Well, that still leads to 60 million errors. That's pretty big. All this seems simple, excuse me. But there are regions in the genome that are hard for certain instruments to sequence. I'd say, I used to work at Illumina Ventures. Illumina sequencers are very, very good, but they have issues in certain regions of the genome and sequencing different regions of the genome. So instead of getting an error in a random 1% of your whole genome, there's most likely a bias towards having 1% errors, 60 million errors in the same region of the genome. And there's there's ways you could try to mitigate this, like higher coverage. So you might have heard 30x coverage whole genome sequencing. That just means you're sequencing your genome over and over 30 times so that you can have some overlap between the errors and then, basically close that gap by sequencing over and over again to take these errors and shrink them down. But the point is that bias is intrinsic to each technique, and even with something like whole genome sequencing, you're almost always going to get the bias and the errors in the same region. So you have to familiarize yourself or talk to knowledgeable people to learn about each technique that people are using in deriving their output and figuring out where the intrinsic biases lie in each of the technologies. I'm not an expert at everything. I have to talk to a ton of people because during my PhD I've only used certain techniques. So everything else I'm not familiar with all the biases that are hiding in every other technology. This is just a very important part of why we have to talk to real experts. But back to absolute bio. So we talked about gene expression, and let's say they're looking for RNA. This is a microarray which can be used to measure gene expression, genes, etc. Not going to talk about any details about microarrays. There's just saying that there are other tools out there to measure different things like gene expression. But if we think about this again, so let's say there's 20,000 genes that are probed. Remember that you need to multiply the 20,000 by many thousands to get the total count of RNAs. And it's impossible, I'd say impossible for most technologies to capture all of these RNA molecules. So let's say that we're capturing 30% of the total number of RNA molecules and 70% are not captured. And let's say in this case, there's a random sampling of all the RNA that's out there. So that sounds good, right? You're capturing 30% of all the molecules, but at least it's random. It's not like the whole genome sequencing or example that I just gave where you're always biased in the same region of the genome. 30% random sounds pretty good. But the thing is, there's bias here too, right? There's biological bias. You're going to bias yourself towards the genes that have more copies of RNA. Some genes have 100,000 copies of RNA and some might only have 100. So when you're capturing randomly 30% of the genes that are expressed by these 20,000 genes, chances are you'll see many RNA molecules of the highly expressed genes and none for the lowly expressed genes. So this can be an issue, or it might not be an issue. You have to think about the context, right? You might only capture 20,000 genes, but maybe these contain the most relevant genes for a disease, and 70% that you don't capture might not be relevant. So in reality, it doesn't actually, almost never works out that way. But the point is that you just have to understand the biases and incorporate this knowledge in your evaluation of a given company or technology. Because even bias might not be a deal breaker. You want to look for consistency. In the X-ray example for the deep learning computer bias that I explained earlier, that bias might not be a deal breaker if you use that particular algorithm just for one manufacturer of X-rays, right? So it can't detect the differences between two different X-ray manufacturers if you're only using one X-ray manufacturer, and it can just tell you the disease versus healthy. So that's fine, right? From a product perspective, that's actually fine. So you should know where bias is hiding, but understand that you're not looking at bias as a deal breaker. You're just looking for adding to your repertoire of knowledge in your evaluation of a company and technology. All right, so when are great samples not great? We talked about all of the different inputs, the variables. Let's talk about the actual samples, because that's very important as well. So Absolute AI said that they use 200 doctor annotated samples to train their algorithms, which is fantastic. I mean, it's not big data, but it's nothing to sneeze at, right? 200, I mean, a lot of companies aren't able to collect 200 samples. So these we talked about true positives before. These true positives, the actual disease population, came from doctor annotation, which is pretty good. But look at the actual sample itself. Turns out there's only celebrities in this sample, right? So if they're the same socioeconomic class with the same kind of X factor in that Absolute AI is an anti-aging company, but they chose a population of people in their sample that doesn't seem to age, then the patients are not actually representative of a targeted population. And that's an issue. And the other thing is, like, the doctor annotation is fantastic, but also look into who's doing the annotation. If it's one doctor that's diagnosing the entire sample population, then there's bias that's inherent to that one person and how they view a disease versus healthy. And so, you can have a fantastic doctor, but it doesn't really matter, because even if you're a fantastic doctor, you will have a particular bias, and that's gonna carry through in what you define as a true positive. And so if you have one doctor in a homogeneous population, you might have a great sample where everything was collected right, the proper RNA, there's no technology bias, and everything sounds fantastic, but the sample itself is not representative of the targeted population, and it could still be garbage. Or not, right? That's why I say context is key here. And if a company, for example, said that they only wanted to diagnose celebrities at $50 million a person, then their TAM or their SAM is still huge, and that's potentially a great business. But if they're saying that they want to target an aging population that's part of the general population, then it's not so great. So you have to understand what the context is. This is seen in everything, right? So bias is everywhere. Just a quick aside here, the last two elections, the pollsters were pretty wrong in determining who the winners were going to be by what margin. And if you actually look at the pollsters that were interviewed, they say that people are truthful. It's just that they're always interviewing the wrong people. So they're surveying the wrong people. And that's why you have these different results compared to the polls. Just goes to show great samples are not always great unless you're actually targeting the people that you want to market towards, or you want to sell towards, or you want to help with a drug or diagnostic. All right, we talked a lot about sample, we talked a lot about variables, big data, et cetera, et cetera. So let's talk about how you can tell if something is real. So validation, which is the name of the game. It's important to remember that there's trade-offs in validation methods. So especially for startups, and as an investor, you always want everything, but a startup usually has to trade off between speed, cost, or control in order to validate the samples and the algorithms and whatever technology they're coming up with. So a company like Absolute AI, where they're trying to split the ageless from the aging populations, they have usually two different ways of validating, using retrospective data or using prospective data. And there's pros and cons to both of these. Let's start off with talking about retrospective data, which I think has a bad rep. So retrospective data means that you're literally using a data set that has been collected, usually by somebody else in the past. So the data set's already there, collected, and you're just using that previously collected data set to train your algorithms, to run different tests, with your technology, et cetera, et cetera. But it's pre-existing data set. It gets a bad rep because the company has not controlled the samples that they're collecting, but really when set up correctly, you can get similar results from retrospective validation as prospective. You can still blind your sample, you can test enough patients, you can still have a diagnosis, right? You have your true positives typically, you can have control groups, and here's a few things that I look for here on this slide when companies show retrospective validation of their technology. Like quality of data, sample size, sample breakdown, who's actually in the sample, how do they blind things, and then what was used for training versus validation of their technology. At the end of the day, did they measure what they actually needed? And even if they have less control over what's collected, it doesn't matter, because you can, if the sample size is big enough, then you can still use this all and kind of break it down in the same way to train anything that you want or test anything that you want. Blinding actually ends up being a problem. We'll talk about that in a second. On the other hand, prospective data, which is what everyone wants, it's gold standard for a reason. Right, you have the ability to control everything about what you're collecting, so you can choose like what patients you want in the sample by having inclusion/exclusion criteria. You can choose how many people you want to test or you want to collect for your training of your algorithm, so you can control things like the statistical power. You can set these up all over the country or the world. From a geography perspective, you can control how long you're tracking these patients. So if you want longitudinal data to see how patients are doing 2 years later, you can do that, and you can include that in your clinical trial. The big downside to prospective data is time and cost, right? So these things are expensive when you're paying to do it yourself, and time is a limiting factor because you have to wait for patients to actually have things happen to them. But here's a few things I look at for prospective data. I mean, if a company does have prospective data, it's usually fantastic for them to have, but there can still be issues with how they've collected the data. So I look at things like recruitment centers. Where are they recruiting from? Is their sample going to be inclusive of the patients that they're going to target later on? How many trial arms do they have? Do they have enough people to statistically power a small difference that might happen? What are the actual endpoints that they're looking at, and what's the duration? The thing is that when you're looking at prospective or retrospective data, at the end of the day, this is a de-risking game. So the question is, did they actually measure what they needed to do it in the right way? And once you have that information, you basically collect it and shove it in your repertoire, again, your repertoire of knowledge that you use to actually think about whether or not you're de-risking something from the company. So as an investor, you're trying to figure out, okay, how does this fit into my my thought of whether or not this company is investable? I'd say that retrospective data, prospective data, it's all good as long as everything is done well. But at the end of the day, it's not whether or not it's done well does not decide whether or not you invest in the company, right? It just becomes a probability of risk that you are breaking down into figuring out whether you want to invest in the company. And I'd highly recommend this book called Thinking in Bets, written by a World Series of Poker champion, Annie Duke. She talks about how you assign probabilities to risk in everyday life as well. Okay, that's perfect. I think that's about 30 minutes. Here's the second kind of obligatory cartoon. to summarize this presentation, and let's go to a break.